Okay. Hey, I am back with the tutorial where we picked off, or yeah, left off. Sorry, words. But we were looking at that football video, and we were looking at running backs versus defensive players, inertia, laws of inertia, motion. So the larger the player's mass, we know the greater the inertia. That means a player with a larger mass has an advantage in the battle of inertia during an attempted tackle. He's more likely to keep moving in the direction he was going, right? You won't see a 104-pound running back in the NFL. Even if he's fast, his inertia would be overcome by the inertia of a 250-pound linebacker running at full tilt. You know, these are big guys and they're fast. So a ball carrier who knows physics will realize that any contact with an unbalanced force will change his direction and inertia. So in order to get down the field the fastest and score, he often needs to minimize contact by changing direction. So you see people cutting and dodging opponents, and while making a cut to the left or right will create a change in inertia. That change will be less than the effect of being hit by another player with nearly equal inertia and mass. So even though he's moving around and that's changing his inertia, that is better than being hit by another player of the same size. So minimize contact to keep moving forward in football. Now we're going to look at equilibrium. Equilibrium, according to Newton's first law, an object remains in its state of rest or motion unless acted upon by an unbalanced force. Conversely, if all forces acting on an object are balanced, the object stays at rest or in constant motion. When forces are balanced, the net force acting on an object is zero, and the object is said to be in equilibrium. An object in equilibrium continues in its current state of rest or motion and maintains a constant velocity. So take a look at the diagram to understand this concept. There are four forces acting on this object. The vertical forces are the force of gravity that exerts a downward pull, and then there's an upward force exerted by the surface on the object. Because these two forces have equal magnitude and are acting in opposite directions, they cancel each other out. The horizontal forces acting on the object also have equal magnitude and are acting in opposite directions, canceling each other out. So the net force acting on the object is zero. It is at equilibrium. Let's look a little deeper at net force and equilibrium. Static equilibrium. The state of equilibrium can be one of two types: static, which is standing still at rest, or dynamic, where it's moving, but everything's in equilibrium. Now, static equilibrium is when the net forces acting on an object is zero and the object is at rest. So think of your laptop right now, your phone. If it's sitting somewhere, everything is in static equilibrium. And in this picture, we see a computer monitor. There's gravity pushing it down, but there's also the table exhibiting a force in the opposite direction, keeping it at rest where it is. These two forces that are equal in magnitude and opposite in direction keep this object where it is. That is static equilibrium. Dynamic equilibrium is when an object in motion with a constant velocity is said to be in equilibrium. So the net forces acting on the object is 0, but it's still moving, okay? If it has a constant velocity, that means that the net forces acting on the object is 0, and it's just moving without a care in the world. That's the idea you kind of want to have. This idea can be illustrated by a car moving down the road with a constant velocity. The engine applies a forward push on the car. Friction between the wheels of the car and the road, along with air drag, acts in the opposite direction. Friction and air drag balance the forward push of the car's engine exactly. So the velocity of the car neither increases nor decreases, but it remains constant. The car is said to be at dynamic equilibrium. In other words, when the net force acting on an object is 0 and the object moves with constant velocity, the object is at dynamic equilibrium. So here, of these diagrams, which diagram is in equilibrium? Okay, which have equal and opposite forces? Well, this one does not. If 30 newtons are pressing down, but only 20 newtons are pressing up, that object is not in equilibrium. Here we just have one force, but no opposite and equal force. So not in equilibrium. D, we have 4 forces, but they're not equal in opposite directions, 30 and 50, 50 and 30. That is not in equilibrium. And finally, C is the correct answer. The net forces are 0 because we have equal and opposite forces in either direction. So here's the problem-solving strategy. So first, you list all of the known and unknown quantities of various forces mentioned in the problem. I would suggest drawing it out. If you're a visualized learner, that's a good thing to do. You want to see the object and the forces acting on it. And there's a way to do this, and it's called a free body diagram. A free body is any object with forces acting upon it. And you list all of the external forces in the X and Y direction. So think of it like a graph almost. And you want to think of these in X, Y. So you can think of the sum of forces equals 0 in the X direction, and then the sum of forces in the Y direction as 0. So you list the X and Y components in 2 columns, and then you carefully check that you have used correct positive or negative signs for the forces. And then you use these equations to solve for which forces there are. If you know something's in equilibrium, you can easily find what's the missing force. So here we go. Here's an example. A 2,000 kilogram box sitting on a table is pushed with a force of 12.10 newtons. Here we go. We have a 12.10 Newton force applied from the left. If the friction force is 0.1 times the normal force, how much is the net force acting on the box? The table shows how the forces are acting on the object. So that first force, the applied force, is only in the X direction. There is no Y component. So it's only 12.10 to the right. in the positive direction. There's a frictional force. So that is 0.1 times the normal force. How do we know what the normal force is? Well, the force due to gravity is 19.6 newtons in the down direction. And that will be a negative 19.6 in the y component for the force of gravity. But it's in equilibrium, right? So the force exerted by the surface on the block is 19.6 in the opposite direction, or the positive direction, since it's pushing upward. Think of this like the graph. Positive to the right and positive upward, and negative downward and negative to the left. So if we are given the normal force is 19.6 now, the frictional force is 0.1 times the normal force. How much is the net force acting on the box? So we have 12.10 minus this force due to friction, which is now negative 1.96, since it's moving to the left, right? Okay. So the net force is 10.14 newtons to the right in the positive x direction. And we'll do another example. And I'll write that out in the key, an answer key, I think. Newton's first law of motion applies to objects everywhere in the universe. An object on the moon, for instance, continues to be in its state of rest or motion unless acted upon by an unbalanced force, but the force of gravity affecting objects on the moon is less than that on Earth. Gravity on the moon's surface is about 1/6 of that on Earth. Here we have a lunar lander activity simulation. Encourage you to look at that. Now we're given another question. A car in dynamic equilibrium is acted upon by the following forces. Force due to gravity, negative 9,000 newtons. Force due to friction, negative 250 newtons. Forward force exerted by engine, 250 newtons. What's the value of the force exerted by the ground on the car? So we know it's in dynamic equilibrium, so it has to be equal and opposite to the force due to gravity. So that would be positive 9,000 newtons. So we summed up the forces in the y direction. They have to be 0, so negative 9,000. There has to be a positive 9,000 newtons to make that 0. So in summary, the first law states that an object at rest stays at rest. An object in motion continues to be in motion at the same speed and in the same direction unless acted on by an unbalanced force. Objects resist any change to their state of motion, and that resistance is called inertia. An object is said to be at equilibrium when the net force acting on it is 0. If the net force acting on an object is at rest and the net force is 0, it's in static equilibrium. If the net force acting on an object is 0 and the object is moving with a constant velocity, it is said to be at dynamic equilibrium. Put simply, the first law talks about an object with constant velocity. Just remember that an object at rest has a constant velocity, v equals 0. All right. So I will see you next time. I hope that was helpful. And I think I will go through the mastery tests with you too. All right. See you next time.